So today we're going to cover the mathematical frontiers of HPC. So primarily, a lot of companies are leveraging the supercomputers, and they have different types of architectures. And so when they implement all these mechanisms to handle large-scale data, they have mainly been successful leveraging with computing with memory. And then again, there are a lot of companies that are also pioneering into getting into in-memory computing, where they could leverage large-scale data for different type of applications like plasma turbulence, nuclear reactors, and various industrial applications. So we're going to take a look at to see what are the most hard conundrums that we have in the industry that we can solve with exascale computing, supercomputing, as well as with in-memory computing. And before that, we're gonna also take a look at some of the rise of the supercomputing machines and different types of architectures, that how we have been evolving all the way from transistors, memristors, and neuromorphic computing, various types of in-memory computing architectures. We're going to also take a look at a supercomputer, which is Astra supercomputer, that's built with petascale architecture, and it has been used for plasma turbulence as well as for nuclear fusion. And we're also going to take a look at the mathematical linear solvers with algebraic multigrid methods. Also, we're going to look at a different type of architectures. Most of the time, we're going to be dealing with either convolutional neural networks or recurrent neural networks for solving some of the largest problems with supercomputing and large-scale data. But we're going to take a look at something different that has been adopted, which is spiking neural networks, which pretty much leverages the neuromorphic computing. The neuromorphic computing is another latest technique of in-memory computing, and we see how they have implemented that, and we're also going to take a look at resolving the issues with the MNIST digit recognition. And then again, there are a lot of techniques that can be adopted in terms of parallel programming, massive parallel computing with supercomputing, and how do we do the interactive supercomputing by exchanging the data in memory as well as through different architectures. And we're going to look at different types of libraries for Python. And a lot of supercomputing companies have built their custom Python libraries, which are not something that we regularly have. So they build their own Python libraries, and they build their own PyTorch libraries. They have added several types of additional packages to deal with that. And then we're going to also take a look at the infrastructure of the supercomputing machine, which is Astra, and see how it works and what are the mechanics surrounding it. So again, the quest for supercomputing is not something that is just started now, but it has been there for a while. And basically, initially it all started with implementing a differential analyzer, and that led to building several other application components for radio communications and telephones, because they leverage the same type of architectures. And then again, there was Fuji Electric invented a binary circuit for implementation of a statistical computer back in the day. And then there was a cipher code that was developed with Turing machines, and that has contributed towards the evolution of building the modern digital computer. And again, later on, MIT researcher has come up with ENIAC, and so that has led to another whole different generation of computer programs, adding different components and infrastructure to improve the performance of the digital computers. Again, there are a lot of things that have been implemented for military applications in terms of shooting down the planes, or simulation of trajectory paths, or moving flight calculations. All of this have been implemented with advanced digital computer. So as the needs arose from various applications and industries, and during war times, so these all have led to the evolution of raise up the supercomputing machines. It's not something that they envision that they need to have so many types of applications, and it's not something they envision where they need to handle different types of large scale volume data. And that's how they started evolving various architecture. Then there was John von Neumann actually has created a completely different architecture where it started building something called JONIAC, and that's basically an electrostatic storage tube that can store large volumes of data. And eventually, the Oregon National Laboratory, they want to leverage, based on von Neumann's architecture, to see if they can implement for their nuclear reactor design. And again, the US Air Force has also implemented a project MITRE, and that has been there for a while, and there have been a lot of applications that have been developing for supercomputing. And Oak Ridge National Laboratory has built another logical engine called Oracle, not this, the Oracle that we have right now. I'm talking about the Oracle Oak Ridge Automated Computer and Logical Engine. And then again, the Federal Aviation Administration continue to support the MITRE for various type of automations and air traffic control operations for further development of US military command, control, and intelligence projects. So there is a special architecture on ARM, which is a lightweight processor, and that can perform various types of in-memory computing operations. And all we do is it supports TensorFlow with Onyx architecture and PyTorch. And there are several neural network APIs that have been built by the ARM, specifically for people running on ARM. So now you must be wondering why we're talking about ARM, because ARM is such a lightweight processor, and it can just work on mobile machines. It doesn't really solve some large-scale data problem. But we're going to take a look at how we can leverage the lightweight processor ARM that only works on mobile, although we're going to scale it up to build a supercomputing machine and see how it can resolve the problems with that, and how it is easier to transfer the data in terms of in-memory architectures between multiple nodes and clusters to solve any of the problems. So fundamentally, the entire revolution of supercomputing movement has begun with Cray that has led the movement. And so primarily it has moved all the way from vacuum tubes to magnetic switches and transistors. A large number of corporations already started leveraging these magnetic switches, moving from the vacuum tubes. We can take a look at like GE, Raytheon, Engineering Research Associates, IBM, Honeywell, and Xerox. All of them have been leveraging the magnetic switches, a giant leap from vacuum tubes. And CDC also has been leveraging magnetic switches. And so ever since the Cray started releasing those supercomputing machines, there's a lot of flurry of activity that we have seen with Northrop and Lockheed Martin, University of Illinois, and National Bureau of Standards. All of them have come together to design their machines with these architectures. And the pioneers have been Los Alamos and the Livermore, who are interested in building the supercomputers for weapons manufacturing. And the next generation of supercomputers actually started leveraging these type of circuits that actually work on the magnetic switches. With in the later years, these circuits that they built were come to known as integrated circuits. So that's what we call right now the integrated circuits. So basically, again, integrated circuits have different types of ICU designs for processors, like maybe for GPUs, for CPUs, for FPGAs, for ASIC chips. A lot of integrated circuits that can be leveraged as, as part of the neuromorphic computing, which is an in-memory computing, where it can be implemented for supercomputing. Again, as we have seen, the flurry of activity has been continuing. The Japanese supercomputing manufacturers have actually started the vector-based computing, because a lot of times, it wasn't easy to solve the linear solvers and the mathematical problems, because the floating operating pointers that where people are programming are only having limited capabilities to perform the arithmetic or calculus operations. hence then you needed something like vector-based computing where they could perform large-scale mathematical computations that could help them to perform and resolve some of the most difficult conundrums. And so that's when actually Cray has come up with a Cray 1, which is basically 88 megaflops peak performance, and that can actually perform 1,000,000 floating point operations per second. So that actually helped them to solve a lot of the problems, maybe for a nuclear reactor. So we're talking about nuclear fusion or the plasma turbulence or performing lots of simulations, because back in the day, before the momentum had started with the deep neural networks, there were people were literally shooting holes into the islands for performing any simulations. For example, somebody wants to simulate a bomb, they have to annihilate an island, create a hole, and then see the impact and understand how much impact it has created and all that. But ever since the deep neural networks came up and then they started integrating with supercomputers and leveraging that neuromorphic computing, so they could perform all of these simulations just on a bomb simulation on a supercomputer. So that tells them, okay, this is how much the impact is going to be, and these are how the results are going to look like. So they stopped bombarding all these islands ever since they moved to these supercomputing architectures. Again, in 81, the CDC has built another computer because they wanted to see that they can go for much larger, performance, competing with 88 megaflops that went all the way to 800 megaflops. And again, they just not only wanted to have large-scale data, but they wanted to start slowly moving towards massively parallel processing capabilities. That means that if you take the data, then we have several clusters of machines that are operating parallelly, so that at the same time multiple operations and calculations can occur. So that's why they started to increase the peak performance of the supercomputing machine so that it can parallelly perform several million floating point operations. And Intel also has come up with some of the architectures for the integrated circuits, and they started building different types of chips, mainly, but they were more consumer focused, where they wanted to power the consumer machines with these type of chips. And Geneva CERN has actually generated a whole lot of www URLs, and it has introduced the HTML because they were dealing with particle physics, CERN, and particle physics also had a lot of simulations it has to generate to see what are the particles we have in the standard physics model versus like you're talking about like bosons or different types of particles like neutrons and all that, and how they would like to compare it to see if they're going to discover any new particle, because there have been a lot of experiments. They're trying to find out, is there anything out of the standard physics model where we can find some additional particles. So for doing that, they have to create a lot of permutations and combinations and trillions of collisions of these particles to see if they are trying to find boson, which is something that they thought was not part of the standard physics model at a point of time, because it's just marked as an additional component to be discovered, but they always knew that the laws of physics support such type of particles existence. So that's where they had to basically perform all of these, different types of accelerators for building the simulations for particle physics. And the National Center has advanced in terms of leveraging most of these supercomputing machines run on the Red Hat Linux. And so again, back in the day, there was a different types of Mosaic or just Linux. Turbulence has introduced the Linux around 29 years ago. And that is exactly when people actually started having an open source computing platform. But again, if somebody wants to build a supercomputer, they need to have more components and more ways of handling it, because it needs scalability and application performance they need to measure. This is exactly how much of data we're going to process, and this is how we can architect to build such type of computing architectures. So again, as we go forward, there was a motley conglomeration of several supercomputing research institutes, starting from Japan, Fujitsu, Mitsubishi, and NEC, Toshiba, Hitachi, and Oki. They all have banded together, and they just wanted to launch a national super speed computer project. And they started building their own supercomputing machines, all of them banding together, a single machine where they could put all of the components and run some arithmetic operations to see if it is scalable. And Intel again started moving away from consumer side to commercial side, and they started manufacturing some of those chips that can support different types of supercomputing applications. And they started building a 16-node cluster that just cost around 40,000 back in the day. And that's when Intel actually shifted their focus from consumer to commercial side. And again, as we take a look at the in-memory computing, there have been a lot of inventions that have some of the most brightest and brilliant minds over the past few decades have built up all of the spiking neural networks, transistors, memristors, and neuromorphic computing, all put together to kind of come with the paradigms for in-memory computing architectures. And so if you take a look at ARM processors, they are very much, they can implement this type of spiking neural networks, and they can also implement neuromorphic computing architecture. A lot of companies do that, like Xilinx, ARM, and Intel. They all have been implementing several types of architectures for neuromorphic computing, and people have been releasing their own chips as well. And that's where they want to see how they can operate on the spiking neural networks. So let's take a look at how we can, how we have come all the way to the spiking machine intelligence. So then, so in AI, there wasn't much going on up until 1940. There were a lot of different types of knowledge-based mechanisms, hash-coded rules, millions of hash-coded rules to see how they can run several rules and conditions. Based on each condition, the program is going to trigger and give some type of an outcome. But that wasn't fulfilling the dynamic situation, because AI is where we feed the data inputs as labels, and the label data needs to be processed, and it needs to produce certain predictable outcomes. And we can't always predict, only a certain amount of combinations that can produce. So that's where it went into a dark era up until 1940, because they were trying to leverage those type of mechanisms where they can code all of these millions of rules. And then they realized that probably isn't the right mechanism, and then they need to probably come up with some different architecture that can support the machine intelligence. And that's when they actually started inventing, Walter Pitts and Warren McCulloch has invented the ANNs, the artificial neural networks. And basically the way they did it is they wanted to simulate and see how the neurons work in that, because the way neurons work, they operate basically taking an input, and then they process the data coming through the inputs, and then again they produce the output. But again, for the mind, it performs millions of operations that are like billions and billions of neurons. There are like 87 billion neurons in human mind, and they all perform and process massive parallel computing to produce this type of outcomes in terms of how a person comes to a predictive outcome. But coming to neural networks, the way they could not make it work, because every time they run through it, they're gonna start getting some errors, and they do not know how do they go and rectify these errors so that the entire algorithm works perfectly. So that's when they started thinking about this back propagation algorithm. So basically, they need to update the weights of each neuron. They need to activate some functions, and they can get the and this particular back propagation and forward propagation has not only been implemented for conventional, convolutional, and recurrent neural networks, it also has been implemented for spiking machine intelligence for the spiking neural networks, which is primarily very important for in-memory computing for neuromorphic computing. And again, as we started moving towards the different types of architectures, von Neumann's architecture helped to a certain extent for building those electronic digital computers. And then again, they started building the transistors. Walter Bretton and William Shockley, and that was the first transistor that was ever invented as part of the Bell Labs. Uh, very expensive back in the day, and again, there was a need that arose for computing machinery and intelligence paper. So why do we need the machines to think, and what's the rationale behind this machine intelligence? And there was a paper produced, and that's when slightly earlier Hebb stated that basically the neurons work together. So basically the set of neurons that work together and produces a predictable outcome, and so on and so forth. So we can see that brain spiking activity as they observe in the brain. Whenever there's more activity in certain regions, they can start seeing that spiking activity occurring in parts of brains. And that's when they thought they could probably leverage the similar type of architecture for artificial neural networks. And they can actually start implementing the neural processes into the neural networks. And that's when they started building different types of architecture. So there's a single perceptron model that was built, and that makes a prediction, and then it keeps improving the prediction until it gets it right by running through thousands of iterations, and it produces a predictable outcome. Till then, it has to run through several architectures. And again, the Stanford researchers have developed Adeline and Madeline architectures that are kind of recognize the phone line with neural networks. So anything they see, any incoming signal or digital processing can be recognized through these type of binary patterns neural networks. And then again, the Bell Labs researcher started inventing floating gate transistors as a synapse, because that's when they started seeing that how many operations need to be performed. And that's very key in terms of performing the arithmetic operations on transistors. So that's when they started moving towards inventing the floating gate transistor, and which is what they wanted to leverage as a synapse for the spiking machine intelligence. And later on, Leon invented memristors, and that is for the electric charge and magnetic flux linkage. And so then so on and so forth. They started inventing the resistors, capacitors, memristors, and inductors. And that's what they started moving towards. In Japan, they invented Kagitron, which is a multi-layered neural network, and it can automatically teach itself, which actually has laid the foundation for building convolutional neural networks. Rimmel Hahn and a few other people have demonstrated how to correctly train these multi-layered neural networks with back propagation algorithm, which is basically calculus and computational graphs. So basically, it's going to produce several graphs that indicate the spiking activity of what is the input spike, and we're going to define several weights in the neural network. And based on the definition of these weights, it's going to process that, and then there is a output spike it will produce, and then there is a memory that is getting transferred through InMemory through the neuromorphic computing. And that's when they start seeing all of this on the computational graphs, and it's just calculus running on computational graphs, and that will tell you exactly what position the predictable outcome is, or which particular neuron has an issue for an update to the weights, and we can go back and update the weights leveraging the back propagation algorithm, and that will increase the spike and improve the accuracy of the predictable outcome throughout the machine learning models. And again, as we start moving forward, then there were several other neuromorphic chips that were invented and pioneered by Carver Mead, and he has predicted that computer would need at least 10 million times more energy for instruction than the brain, because what they want to do is that computer just the brain just operates basically with 20 volts of electricity. That's all it takes to perform all of the millions of calculations. But again, if you were to leverage the same mechanism and run it on a supercomputing machine or any such advanced computers, it would require 10 million times more than the energy per instruction than the brain. And later, the autoencoders were introduced, and they were performing unsupervised pre-training in Ballard. And the autoencoders were very useful because in the later years, they were useful for drug discovery, quantum chemistry, quantum physics, and also for bioinformatics or genetics. A lot of fields, autoencoders have been very useful, especially for unsupervised training. And again, the spiking neural networks were introduced as neural networks based on perturbations for computing. And the LSTM network, which are the long short-term memory, were invented by Sepp Hochreiter and Horen Shibuda. And later, Bayan-Ku has presented the spiking timing. Depends on, there is something called plasticity. The plasticity is basically the amount of precision of a spike that occurs, and it's about the resilience of the neural network to be able to rebuild. The same concept that we have, the plasticity of a brain is about the neurons about to rewire and again recompute it. Because, for example, if somebody makes a mistake in computing something, so the neurons have the plasticity to be able to recompute it and get an accurate arithmetic calculation. Let's say somebody is making a calculation 2 by 2, or maybe like something very complex number. They just come with an error. The ability of the brain to recover and reproduce and recompute that arithmetic operation is the nature is called the plasticity. The same concept has been implemented in the spiking machine intelligence for whenever we perform calculations and it runs into some errors because the weight is not updated or a particular function has not been activated in the neural network. So go back and update that and come back with an update to the spike, and then it's going to increase the synaptic strength so that the synaptic is going to produce much higher accuracy in terms of producing the predictable outcomes. And again, NVIDIA has come up with a concept of the GPUs, and that's when they wanted to leverage them as a parallel computing processors, and then which has led towards the CUDA programming in the later years. The CUDA programming is basically a parallel computing and parallel programming so that it can be done on like C, C++ APIs, and there are MPP APIs, NPI APIs, massive, and they all basically perform massive parallelization of computation so that it's going to break down the whole data into multiple chunks, and it's going to start dividing into APIs and transfer to the memory, and then it gets processed in a specific cluster and machine, and the results are going to be assembled, and they're going to come back to the main source where the actual calculation is occurring. So they're going to accumulate all of those outcomes, and they're going to come back here and get the main predictable outcome from the origin of where the calculation has started. That's the purpose of just think about object-oriented programming, where you have we're declaring a class and we have several methods, and we're going to pass each method to several parameters, input, output parameters, and we're going to get the results back to each method. So think about something like object-oriented programming, where the result comes back to the main class, and then that gets assembled, that gathers the data from all these multiple parallel computing clusters. And that's how it can be leveraged. So again, the neuromorphic vision sensors were invented for that inspired several biological systems, and the fast matrix multiply on commercial GPUs have led to the acceleration of the deep learning algorithms. And so that's when we started seeing more floating pointers of millions of calculations that can be done. And again, Stanford has come up with a neurogrid chip leveraging the analog neural circuits, and generative adversarial neural networks were invented based on those analog neural circuits. So now let's take a look at Spinnaker. Spinnaker is a very specific multi-core super computing architecture that has been built. As we were talking earlier, I mean, what we can do with ARM processors, because ARM processors are just nothing but, some type of processors that do not leverage, heavy applications, because most of the time these are leveraged in any mobile processing units like phones and stuff like that. But Spinnaker actually has taken it to the next level by leveraging the ARM processors, and they have built a whole supercomputer with ARM hardware and 518,000 ARM processors put together as they built this um, supercomputer, and that's called Spinnaker. So basically, if you're taking a look at Spinnaker, and so this is the architecture, and it has the implementation of in-memory computing, because basically they put a RAM, the dynamic random access memory, where it takes a lot of data directly into the memory rather than processing through the conventional disk-based processing systems. Because back in the days, if you see all the sequels and all that, they used to process in 70s, mostly on the conventional disk-based operating system, because there's so much of round-robin trip that needs to occur for each execution of SQL statement from the program. It has to go to the SQL, it has to go to the disk and make a round-robin trip for every SQL executed, which gets really complicated, because if somebody is executing multiple statements on the SQL, then they have to make so many round-robin trips. And that's because of the disk-based operating system. As we started moving towards all the streaming computing machines running on NoSQL databases as well as SQL databases, especially if it is something that's operating upon the memory, it's going to be pretty quick, because everything is already buffered and the data is just in there, and any SQL that gets executed from the program just returns the data right away. Again, it's not the near real-time computing, it is the in-memory computing. The data is just there on the memory, and they can just leverage taking all of that memory. Again, and this is, I'm talking about SQL and NoSQL, but again, we're talking about Hadoop is a similar process because it goes through the disk-based process, but the architecture that are built with, for example, if you're looking at Apache Ignite, which is an in-memory computing platform of great gain, or we're looking at Hazelcast, or a number of other IBM in-memory computing architectures, and then there is also, HANA, high performance application appliance, and all of these have been built on the in-memory computing DRAM architecture, so that the entire memory is in there. And any algorithms we can compute, we can run all the computations, everything is on the memory. It's much faster rather than going to the disk and assembling the data back up from the disk all the way to the memory. So again, if you take it to the next level, and we actually run this in a supercomputer, and that's when they actually started running this Spinnaker, and Spinnaker has been a quite successful ARM-based supercomputer, and they created a grand challenge to resolve by creating the simulations of billions of neurons, because the fundamental objective of Spinnaker is to understand the inner workings of the brain, how the brain works, and how these simulations are occurring, and how they're occurring simultaneously. And because, especially if you're talking about, such a low consumption of the electricity in the brain to perform these type of operations, why can't we just run on lightweight processors, which are very energy efficient, and we don't really have to run with a lot of power? So that's when they actually started moving towards the ARM processors, which are very lightweight and cost efficient and energy efficient. Because they're also releasing laptops on ARM, which could literally run for a whole day, because we are bringing the mobile processor into a consumer. So they took it to the next level of supercomputing. So that's when it is completely energy efficient, and it runs much more faster, and it also produces some high performance computing applications. And especially the purpose of this project is to understand how the stochastic communications are occurring in the brain, because whenever these operations occur in the brain, they have very complex structures and very sporadic, very dynamic. It's not like we have a static, uh, communication that is going from a synapse to another synapse, or going from a neuron to another neuron, or a region of neurons that are spiking up, again passing to the next set of neurons. So how does this happen so faster? So they want to understand all of these neural networks. So that's when they implemented this for high performance computing application. And so this is where you guys can take a look at it. There's also code that we can actually run. Actually, in my upcoming book, I'll be implementing some of these architectures where I'll show how to run the spiking neural networks and get, the neuromorphic computing, in-memory computing, and leverage that with, couple that with neural networks, and how we can leverage, getting the outputs and arithmetic operations much faster. So that's what the future is all about with neuromorphic hardware, because it's all going to be in-memory computing for artificial intelligence and machine learning and deep learning applications. And again, there's another initiative that was started by a human project, and they started building brain-scale-less neuromorphic chips, where they've been successful with deep spiking neural networks. That's the first success with deep spiking neural networks. And here, the example we are seeing here on the left-hand side is basically just running a digit recognition classification, just to identify, how do we classify a specific digit. But again, the other project is to simulate the entire billions of neurons from the brain on the supercomputing machine. And they would like to know by 2023, how does the brain function? And they're also collaborating with other companies here. For example, like there's a brain institute that has funded about $1 billion to understand the inner workings of the brain. They want to decode the brain and try to build the chips that can leverage the architectures of the brain. So whatever the outcomes they gain from this project, they're going to contribute to the brain, human brain project. They're going to contribute to that. That's where there's so much of collaboration that's occurring around the globe to decode the brain together. So again, as we said, that what are the things that we can achieve with in-memory computing, especially with neuromorphic hardware. So if you're talking about plasma turbulence and linear solvers are quite complex algebraic solvers. And so basically, they're going to perform several simulations to see how it goes through multi-grids and produces the outcome. So again, when the humans always wanted to invent this energy, and when they wanted to invent the energy, they just don't want to go to the traditional energy, because a lot of issues with traditional energy and outages, and also they cannot even produce the amount of power that everybody needs in the world. So that's when the need arose to build a nuclear fusion reactor. And so again, you will get all of this in my book with actual implementation algorithms and stuff. But we're going to take a look briefly from the time perspective. So basically, the way that they want to do it is like sun is producing the fusion, and how is it able to produce take the helium and produce the fusion reaction. So that's when we get all of this nuclear fission. And so when can we replicate this in a lab? Can we recreate the nuclear fusion? And so can we create the unlimited energy what sun produces? That's the aim of this lab. And that's what when they started doing, because when they try to experiment with such type of creating temperatures that are nearing what heat that gets generated at the center of the sun, but basically they needed to build tokamaks, which are basically that contain the extreme temperatures of the nuclear temperatures, and that's when it creates the plasma turbulence. So the plasma turbulence will require multiple nuclear fusions to occur, and they primarily rely on the the high performance computing and in-memory computing. And that's when we can gain the insights into fundamental physics to see how the nuclear fusion can be recreated with extreme temperatures inside a lab for us to recreate, such unlimited energy for the human whole, humankind. So that's when we wanted to, do this understanding the core plasma turbulence. And again, there are a lot of supercomputing platforms that have tried this earlier. For example, Trinity, there is a supercomputing architecture that has tried that before to see, because it requires creating a lot of Monte Carlo simulations. The CFD, the computational fluid dynamics models, and then they have to create the hydrodynamics, molecular dynamics, and linear solvers. All of that needs to be created in order to understand the turbulence of core plasma. And a number of laboratories have come together, like, for example, Sandia National Laboratories. And so they actually have built their own Astra supercomputer, similar to what we've seen with Spinnaker has been successful in UK. And now Sandia National Laboratories have built, that's also right now in the top 500 supercomputers. It performs extremely well in terms of performing simulations of trillions of particles for the plasma turbulence for nuclear fusion. And earlier they tried with 3D supercomputer, and they wanted to go with a lot more scalability, and then they moved to Astra supercomputer for nuclear physics and high energy density particles and hydrodynamics and turbulence and atomic physics, solid state physics, and high explosives. So that's when they started leveraging this, and they actually have the earlier Trinity, they were able to break the world record for bomb simulation for cache of US nuclear weapons. And the scientists also replicated the Fermi acceleration, because the Fermi acceleration is something we usually see that happens in a supernova. So a supernova goes explosive in different parts of the galaxies. There's so much of energy that's emitted, which the sun produces in billions of years. It just generates in a fraction of a second. But they wanted to see how to replicate this Fermi acceleration. So the specific Fermi acceleration is the part of the supernova in particle physics, and they wanted to see how to reproduce it. So the Los Alamos National Laboratory and Lawrence Livermore National Laboratory and Sandia National Laboratory, all of them have banded together, and then they were able to reproduce this Fermi acceleration to see how it is actually working, and to understand how the particles oscillate back and forth and gain the moment. And that's exactly how they try to understand the plasma turbulence. Again, when they have run this on the ARM architecture with the Astra supercomputer with neuromorphic hardware, which is basically nothing but in-memory computing, they have seen all of these outputs. Like, this is very significant acceleration speed. We are looking like 1.6x, 1.45x, 1.3x. This is basically something that could not be accomplished with conventional disk-based operating systems or different type of mechanisms. So this is a significant outcome, solving the linear solvers, especially in the algebraic calculations. And the way that they actually started creating.
Hi, we have about 5 more minutes in this session.
Okay. So yeah, I mean, again, you can get most of this information from my upcoming book, and you can also take a look at different types of implementations in TensorFlow and PyTorch, how to implement these type of architectures. And so this basically gives the petascale architecture of at Sandia National Laboratories, and that will solve the linear systems and basically on the unstructured grids. And parallelizing this algebraic multi-grid could be very challenging, because they have to build and come up with their own mathematical library called Hypray, which is basically a scalable linear solver. and they develop parallel algorithms and algebraic methods. And so they have shown a lot of, there are multiple predecessors for Astra, like on-hammer and APM HPXG and Sullivan supercomputer, KVM Penguin, and they have come up with a specific hardware architecture to solve most of these problems that we are talking about. And again, also ARM has partnered with HP on getting the in-memory computing for the compute nodes, and they implemented the Thunder processor with memory bandwidth, and so most of them are for National Nuclear Security Administration, because when they transport the nuclear weapons in the trucks from a place to another place, they need some nuclear security, and that's exactly what they try to solve this problem. And again, it has now ranked 36, the HPC system on the ARM computing architecture right now in the top 500, and it has reached a teraflop peak performance. So now coming back to supercomputing. So again, coming at the programming level, we looked at the architecture level of how we can accomplish this. And so Jupyter Hub, and basically is Jupyter Lab. So again, we can also integrate this for any application. We're talking about streaming computing machines for IoT to get the real-time events processed as soon as we get the data coming through. And we can also process this for any supercomputing applications based on the distributed parallel computing. And so there are different types of shells and channels available, and we can accomplish this on Jupyter. Again, they have built their own Jupyter Lab environments. Most of these labs we are talking about, for project-based, because it's more like an enterprise supercomputing scale Jupyter Lab they need. So they have to build their own libraries. They have to build their own parallel distributed computing scientific applications for that. And again, how it performs, I just gave you a description of a sample of a Jupyter notebook, and how all the communications occur in terms of the task controller. The task controller can leverage the parallel task for in-memory computing, and it can spawn several tasks, which we just discussed about the MPI. So MPI is a parallel computing technique of supercomputing. And again, we need C++ APIs for that, so that we can process any functions from NumPy. Again, if you're doing Python, you can go for NumPy, or if you're going for PyTorch, you can go for tensor computations. So this is primarily the architecture of the Astra supercomputer we just spoke about. So the peak performance is 2.32 petaflops, and it has a total memory of 324 terabytes. So that's the memory we're talking about, in-memory computing here. So if you break down, and again, the peak performance, they also have started adding more and more RAM for processing all of this data through the supercomputing application. And you can take a look at it. You probably may not get this information. You'll get only in my book. You will not get this in Google or somewhere else.
All right. Thank you, everyone, for joining this talk tonight. Tomorrow we will start again at 7 a.m. Pacific Standard Time, and we hope to see you then. Thank you for joining.